Thank you, Alan. So there was a lot of meticulous planning that went into this so that everything would go nice and slick, and as you can see, nothing has gone slick. But that's quite a nice way to start off, because now I don't have high expectations. As Alan said, I'm an industrial mathematician here, and there are quite a lot of us in Okiam here. And what we do is we work with lots of industries who bring along problems, and then we work on these and find solutions that can help to advance society or technology. And what I'd like to do in this talk today is tell you some stories about some of the industries that I've worked with and the kinds of techniques that we've used to solve some of the problems that they present. So, what I want to do to start with is motivate this idea of going backwards in time that is in my talk title. So let me try and switch to the camera. Yeah, okay. So what we have here is a container, cylinder container, and it's full of glycerol. So this is the kind of stuff, if you've ever had a sore throat and gone to the pharmacy, you get honey, lemon and glycerin, it's that kind of thing. So it's a sugar solution and it's quite viscous, quite sticky. And that's inside this container, and then inside the centre of here we have a cylinder, and when I turn this dial here, this handle, it spins the glycerol around, and hopefully you can see that. This glycerol is clear, so you can't see anything going on at the moment. So what I'm going to do is I'm going to inject some coloured dye in so that when I move the handle you can see how it smears out. Okay, so let's have a go. I'll try and inject some blue dye first of all. I'll inject it and then have a look and see if it's in the camera shot or not. Can you see that? Oh yeah, you can see that. It's a little bit faint, but you can see it. And then I'll try some red dye now. Get this here. And I'll try and be a bit more creative with this. There we go. Ooh. That was supposed to be an M, but we've got a little bit of a pattern there, okay? So what I'm going to do now is I'm going to mix this all up as we go like this. You should hopefully see this. Yeah, you see the camera updating, and I mix and mix. And then I don't really need to go too far before it's all the way come round. And actually you can't really see much here. You can still see smears on here. So now we ask the question, what if I go in the other direction? So in some mixers, you mix in one direction, then you mix in the other direction, and it mixes things up even more. So the options are here, it's going to mix even more, it'll stay about the same, or it'll completely unmix. So and the blobs will go back to how they were again. So that's an option. So just to check hands, I'll give you the three options. So mix more, stay the same, or completely unmix. So put your hand up if you think it'll mix more. Okay, quite a lot. Stay about the same, and completely unmix. Okay, so we have a big number of people who say it's going to completely unmix. So if I spin this round now the other way, turning like this, then sure enough, it completely unmixes. And actually, it's pretty robust, so you can flick this round and go backwards, and you can do this pretty fast, and it unmixes every single time. So this is perhaps not to this audience, but perhaps to the other audience, quite unexpected. You might, when you give a maths talk in the maths department, you're always going to get people who know the answer. But this is kind of surprising, and you can have a go at this. If you didn't believe me and thought I was doing a bit of a trick here, you can have a go yourself. You can just take a beaker, go and buy a beaker, put another beaker inside, like a cylinder, and get some glycerin from a pharmacist, and then put the colour in and turn it round and turn it back, and you'll get this kind of feature. So it's kind of interesting. And so that's the idea when we want to kind of tap into this notion of going backwards in time to see if we can solve some industrial problems using this. So if you're interested in looking this up, it's called a reversible Stokes flow experiment. If you look this up on Google and have a look on YouTube, there are some nice videos of this. So how is this going to help us with the kinds of industry problems that we're working on? Well, here's a box of cereals. This is called Nesquik cereal. And if any of you have young children, then you might be familiar with this because they might be making their name when you're trying to get them off to school in the morning or something like that. So the idea with this is that you make these things in a similar way to a Play-Doh fun factory. And again, if you have small children, you might be familiar with this thing as well. So what you have here is some Play-Doh that you inject into this device here, and then you squish it out, and you can make stars, or you can make crosses, or you can make these holy shapes, and then this funny shape here. Now the good thing about Play-Doh is that it's almost solid, which means that when you squish it out, the hole that it comes out of, this nozzle, is pretty much the shape of the thing that you get. Now with Nesquik cereal, what you're squeezing out, it's the same kind of idea. You squeeze it out of a hole, but the Nesquik cereal is a hot, bubbly liquid. So when it squeezes out, it doesn't behave like this. So this is a simulation done by Michael, who is sat there, to give us an idea of exactly what does happen. So here Michael has been trying to make Mickey Mouse, if you can see that. So we start off with Mickey Mouse at the start here, but because it's a cereal molten mixture, it oozes out, and you actually lose Mickey as you go along. So this is no good. And this is no good because it means that if you want to try and make particular letters, then you're not actually clear what hole you should pump this cereal mixture through. Because, for instance, if you pump it through an R shape, because of this evolution, you don't end up with an R. In fact, one of the features you notice here is that the hole closes off. And another feature is that they're not very regular, all of the letters. So we have another experiment over here. This is with an overhead projector. This is very old school, but hopefully we can rely on the old school kind of stuff. So what we've got here is a cookie cutter. And I'm just going to put some more, I like my sugary solutions. This is golden syrup. I'm just going to squeeze the golden syrup into the cookie cutter, like so. There. And then I'm just going to take it out. So, what you see here is that quite quickly, remember what the thing looked like? It's like a star shape. It had quite pointy edges. Quite quickly, you lose the points, and you get something like this. So this is exactly the kind of thing that's going on with the Nestlé problem. It's coming out, and it's changing, so you don't get the star that you started with. Now, if we were to try and model this mathematically, this is what Michael did with this. He just took what are the Stokes flow experiments, that's exactly Stokes flow equations, that's exactly what we used to model this here. Then if I give you an initial shape, you can tell me how it evolves. So I could say, what does it look like 10 seconds later, a minute later? That's called a well-posed problem. Now if I take this shape here, and if you hadn't watched me do that experiment and I said, what did that look like when I started? You wouldn't be able to tell me. It's lost all of the features. So if I want to go backwards in time, this is what's called an ill-posed problem. And this means it's mathematically challenging, impossible to solve, because we can't just run time backwards to work out what shape we need to start with. But this is exactly the challenge that Nestlé wants here. They say, we want to make an R. What shape should we start with? And you can't say, well, let's start with an R and just run time backwards. So the kinds of mathematical tools that we're going to introduce in this talk will be to see how we can get around this problem and work out how we can make this kind of cereals. So this is the idea that we have. We want to try and make better letters here. Now this is quite a hard problem because, as I said, it's a bubbly cereal mixture. So I'm going to take a step back and consider glass manufacture instead. Now glass manufacture is exactly the same process. It's an extrusion process, but glass is easier to work with than a molten cereal mixture. So if you want to make all of these products here, anything from these optical fibers to test tubes and little medicine vials here, they're all made in exactly this same process, this extrusion process. And you take your molten glass and you pump it through a hole here and you pull vertically downwards. Now notice all of these are circular, and that's good because that means that it doesn't matter how much you pull, it's never going to evolve from a circle. Everything wants to end up as a circle. If you look at this here, it's going towards a circle. Now, this was working with a company called Schott. Schott makes glass for lots of different companies, such as Samsung and Huawei. And they asked a very similar question. They said, we don't want to make circular capillary tubes. We want to make square ones, like this. They wanted to make square medicine vials, and they wanted to make square test tubes so they don't roll around on the table. So, and their question was exactly the same. What hole should we pump this through so that we end up with a square? This is my schematic, but we're going to try and find out what that is. Now, we use the Stokes equations again, which are exactly what would describe this, exactly what would describe Michael's problem. But the forward problem is well posed. I give you a shape, I go forwards in time, you can tell me what the shape looks like at any given later point. The inverse problem is ill posed. I give you a shape at a later time, you can't tell me how that evolves backwards in time. So this is a challenge that we want to try and overcome. And the way in which we do this is by making various simplifying steps. And the first one is, we look at this problem, and this is a complicated three-dimensional problem of drawing a tube. Now, the first thing we do is say, let's convert this into slices. So just like I showed you on here, this was on a plane, two-dimensional problem, and we looked at evolution of this blob with time. So let's say we'll consider a time evolution problem in 2 dimensions with the idea that each of these snapshots in time corresponds to a different axial position. So we can imagine stacking these up like coasters to reconstruct our 3-dimensional shape. That's the first simplification. That turns it from a 3D problem into a 2D problem. The next simplification is we say, let's just look at a little bit of this glass tubing here now, in this zoomed picture here. And we model this using the angle, theta, and the arc length, so that's s, as we go around, and time t. So if I tell you the angle at every single point on this glass and at every single time, that's enough to reconstruct the problem. Now what we've done here is we've taken a complicated 3-dimensional problem that is ill-posed for negative time and turned it into a tiny little piece that we're going to reconstruct. And the evolution of this tiny little piece, we can run backwards in time. That's well-posed. So that is exactly what we do. We reconstruct our picture by doing lots of tiny little pieces, and now we start with a square and run it backwards in time. And we get our 2-dimensional slices, which then allow us to reconstruct the 3-dimensional picture. And the interesting things about this are that you can do it for any shape you like. Here I've done it for a square, but you can do whatever you like. And what was a very complicated problem to solve mathematically or to solve using experiments can be written in this little box here. This encapsulates all of the information about this. And this theta s naught here tells you the shape that you want to start with. So you can put whatever you like into this. As an example, here's a funny shape that we might want to start with, a hole shape. What do you think that ends up evolving to? Does anybody know? Someone said a triangle. Any other guesses? What? Mickey Mouse again. Looks like Mickey Mouse. It's a heart. It's Valentine's Day tomorrow. We have to have something. So for those of you who have not yet bought a Valentine's Day present for your loved one, you can come and talk to me and we can make you a Valentine shape, heart shape tube. For those of you who didn't know it's Valentine's Day tomorrow, I have just saved your relationship. But this generalizes a lot more than just what we've shown here. It generalizes into multi-structured optical fibers, and these are pretty big business nowadays. As we're trying to transmit more and more data around, we need to transmit lots of signals in one fiber. So here are 2 examples. This one here looks a bit like a Mercedes-Benz. It's quite hard to see, but it's got 3 struts. So you can send 3 times the amount of signals down this tube. This one here is surrounded by a honeycomb, and this prevents the signal from leaking out. And we can do exactly the same kind of idea with this. How do we make a Mercedes-Benz shape? Well, this one is a lot harder, actually. It's perhaps not what you would expect. it also doubles up as a really nice thing to keep your flowers in. So I'll tip those out. So you can kind of see, this stays in my office, it's nice flowers. This has been 3D printed on Alan's 3D printer. So this is a nice way to visualize these kinds of products when you've made them. Okay, so let's stick with the idea of glass manufacture for the moment. But what you can see and what I've shown you is that this all translates to making the Nesquik cereal. These kinds of ideas, these multi-structured optical fibres, are exactly what you need to make the Nesquik cereal, albeit in a more complicated fashion. Now we're going to move on and we're going to ask the question, how do you make glass sheets for mobile phones? This is a glass sheet that this guy has got in his hand here, and it's so thin, you'll watch in a minute, he'll squish it and it flexes. And I find this incredible. This is glass. You have this idea that glass is very brittle. But this, sure enough, is glass. And we've got some here. You might not be able to see at the back, but it really is flexible. Now, what we did once is my PhD student handed this out for people to have a play around with. But the trouble is, it has a limit of how much you can flex it. So you could hear this cracking sound as it was going around the audience. And then what came back was dust. Or I guess sand. Sand is the raw material of glass. But you can see just how flexible this stuff really is. And this is used for flexible electronics. Samsung released their first flexible device last year. And I believe Apple are going to release one next year. So we're interested in trying to make this kind of glass sheet. And the way in which this is made is called the redraw process. The glass tubes were made using what's called the down draw process. This is called the redraw process. Now what you do here is you start off with a rectangular block here and you feed it down into this heater zone here and you pull it at the bottom with these rollers. You pull and you stretch and it gets thinner and thinner until the product that comes out is the product that you just saw. Now the downside of doing this is if you've ever had a go at making pizza, when you're trying to stretch your pizza out, when you're done, you have a look at this and you've got a fat edge all the way around. That's your pizza crust. Pizza crust is nice on a pizza. Pizza crust not so nice on a piece of glass. So here you get exactly the same kind of thing. When I pull my glass downwards, you get these fat edges. So this is a 3D print of this kind of thing. Perhaps you can't see, but I've started with a rectangle here, and when I pull, I get fat edges at either side. And if you're interested in looking at any of these things at the end, then you can come down. Equally, if you want to play around with this at the end, we can. So, this is a similar kind of question. We want to know, how do we make glass that is completely flat at the end, no fat edges? And these fat edges are bad for two reasons. One is that if you have a mobile phone and it's got fat edges on it, it'll distort your picture. Two is if you have these fat edges, it won't flex, it'll fracture. This is called fracture. But the problem, just like the other one, the other glass problem, the forward problem is well posed. I can take a rectangle here and I can pull and stretch and I can tell you exactly what the shape will be at the end. But if I give you a final shape, it's very hard to work out what shape I should have started with to get that. So here's the question. Rectangle makes fat edge rectangle. What shape should we start with to make a flat rectangle? And we need to come up with another creative idea because we can't just run time backwards. Same equations as we've used everywhere else, the Stokes equations. But we're now going to do something a bit different. What we're going to do is say, if we put this glass in and then we pull it out faster, then it stretches. What happens if we put the glass in and pull at a lower speed than the glass is going in? So physically that doesn't make sense. It's almost like you're trying to push the glass back up into the heater zone. But mathematically, we can choose our pulling speed to be whatever we like. So if we choose our pulling speed to be 20 times slower than the input speed with a rectangle, then what we find is we get this funny shape coming out of the bottom. And what that means is, if we were to start with this shape at the top, this tapered shape, and pull at 20 times the input speed, we should, in principle, recover the rectangle. So does this work? Let's have a try. It does. So here's another thing. So again, you may not be able to see at the back, but we start off with this tapered rectangle now and pull, and what you get out of the bottom here is perfectly flat glass. And so these ideas now are used on your Samsung or your Huawei phone products. So this is how they make the flat glass that goes on the front and also goes on the back and covers your camera. So it's nice to see that the mathematical models that we develop are actually implemented in industry. Okay, so that's been a lot about glass manufacture. I'm going to switch topics now to filtration. Still keeping the idea of this, can we go backwards in time to work something out? This is me at home doing my vacuuming because I'm quite house proud. But I'm frowning as I'm looking at the vacuum cleaner. And the reason I'm frowning is because it's not picking up the dust. So you might say, oh, it's because the bag's full. But Dyson have no bags, and they have no loss of suction. That's my sales pitch for Dyson. That's what gives me my half-price Dysons. So the reason it's blocked is because the filter has blocked. So it's not picking up the dirt. Now what we're working on with Dyson is trying to make a filter that lasts longer. Ideally, lasts the lifetime of the vacuum cleaner, so you never need to clean it. Now, in principle, you're supposed to change or clean your filter about every 3 months. How many of you actually change your filter every 3 months? How many of you actually vacuum every 3 months? Well, that's the idea. So if you were doing as you're told, then you should change or clean this filter every 3 months. If we could extend this so we never needed to change it, that's a good idea. Now, to understand what's going on in a filter, this is an example of a Dyson filter. They're quite fluffy. It's like cotton wool, effectively. And I've illustrated this cotton wool filter in this picture here. So imagine all of these blue circles here are fibres that are sticking out of the page. Okay? Then I'm going to put some dirt into my filter, coming in at the top, black, and see where it sticks. So here comes my dust. And what we see, I'm changing the colours here, and the colour change corresponds to how much dust has been trapped by each of these fibres. And what you see is that the colours at the top change a lot more than the colours at the bottom. And this is generic in filters. If you've ever actually looked at your filter in your car or your vacuum cleaner, and you take it out, you'll find that it's really dirty on the one side, all black, and you flip it over on the other side, and it's all white, it's all clean. And actually, even if you look in the depth, it's all clean as well. So that's indicative of a filter that's not working to its full capacity, because when the top surface is blocked, then it's all over. So we asked the question, could we make a porosity graded filter? And by that, I mean, could we open the top out a bit so that it lets more of the dirt through, so that the filter down here is also trapping dirt? And really what we're after is a filter that traps dirt uniformly throughout, so that when it blocks at the top, it blocks in the middle and it blocks at the bottom, it blocks everywhere at once, and it's trapped all the dust. Now, how do we model this? Well, it's a really complicated problem to model all of these particles, all of these dust particles wiggling around in your filter. But that's not what Dyson cares about anyway. They just care about what concentration of dust do we have, how dirty is your house, and what concentration of dust is coming out of the other side, which we hope is 0. So what we want to do here is use a technique called homogenization theory. And what we do in this is we take this complicated problem on the micro scale and upscale it so that we look at this on the macro scale. This is a bit like looking at the picture, going to the back of the room and screwing your eyes up a bit and getting a blurry picture of this. So that's our idea. And in doing that, what we can do is we can model the macro scale picture that we care about. That's for the fluid flow, in this case the fluid is a gas, and the dust transport within our filter. But then this is coupled to the micro scale, so we don't lose that micro scale behaviour. So here we zoom in and we have the little fibres on the micro scale. And what we say is when this filter has blocked, these fibres are all touching one another. And ideally we want to make sure that these fibres are all touching one another everywhere in our filter. Here we have our green box again that we're becoming quite familiar with now. The forward problem is well posed. I give you a filter, I say this is your dust concentration, you can run it, you can see where the dust will stay. If I gave you a filter, you would not be able to tell me how this filter got into this current state. But that's what we want. We want to say, here we have a filter that is blocked everywhere at once. How should I run this backwards? What filter should I have started with to end up with this? So, this is what we want. If I plot a graph, this is my only graph that I'm going to show. This is the filter depth here. And what we want to say is that at the end point, everywhere looks like this. So if I plot the fraction of the free volume, which is the white space here, compared with the total volume, then I want this to be uniform as I go from the top of the filter through to the bottom. And now I just want to run this backwards in time. And what helps us in this problem to go backwards in time is the fact that we have two distinct timescales. We have the timescale over which a little piece of dust wiggles its way through the filter. And that's about a millisecond or so. And then we have the timescale over which the filter blocks. That's about 3 months or so. So this disparity in timescales that allows us to work on this longer timescale of blocking, which is the one that we're actually interested in, and we can run time backwards on this timescale. So that's what we're going to do. We'll run time backwards, and these are snapshots of the fraction at different points. And this is what we end up with. So sure enough, we want it to be quite separated at the top, because that's where the concentration of dust is the highest. Less so in the middle, and quite close together at the bottom. And with this filter, if we run it forwards in time, then it'll block everywhere at once, which is exactly what we want. So with these kinds of filters, you can get about 4 or 5 times the lifetime out of this. And this is pushing to the limit of the lifetime of a vacuum cleaner. So this is something that we're exploring with Dyson at the moment. Okay, so everything I've shown you so far has been going backwards in time in a quite nice way. We'll go back over to this OHP again. I'm going to do one final experiment here, which is kind of similar to the other experiment, and that is I'm going to blob some more golden syrup onto this thing here. One of the things you notice is that it quite quickly forms a circle, which is showing surface tension at action. And then I'm going to drop another Perspex plate on top. And I'm going to squeeze. Okay. So it's incredible how circular this is. Okay, right. Now I'm going to start to pull these plates apart again. So I'm going to go backwards in time. And you have to think, well, what is going to happen in this case? Is it going to just shrink? Can we go backwards in time again? Well, let's see what happens. So I pull this very carefully apart. Ooh. And ooh. It's quite tricky to do. I also don't want to get it on the overhead projector. So you get something completely different. You get this quite pretty pattern. And if I push again, it all regularizes again and you go back to the circle. So this is repeatable. You can get some really quite nice patterns coming out of this. This is called viscous fingering. So this is an example. I can't see anything now after staring down on that. Where's the stage? So this is an example where you can't go backwards in time. The inverse problem is very different to the forward problem. And this is a big issue in the oil industry. So let's imagine that I've got some oil down here, and actually we're running out because we've used up a lot of this. So this guy is looking quite sad because there's not so much oil. And then someone else comes along and says, I can help you. What I'm going to do is I'm going to pump some carbon dioxide down here, And the carbon dioxide is going to push the oil and you're going to get more oil out of here. That's the idea. So this guy starts doing that. But you get exactly the same picture that we got over here, because this is air going into oil, just like here we had air pushing into golden syrup. So this air pushes, CO2, and it just pushes straight past the oil and goes straight up here. So you've got this one guy here. So this guy here is pumping CO2 down. This guy here is collecting all the CO2 that this guy here has pumped down, and then after a day of work, they go home and think they've done a good job. But this is a really difficult issue in the oil industry because of this idea of this viscous fingering. Trying to push a less viscous fluid, in this case this is CO2, into a more viscous fluid, you always get these viscous fingers. So this is an instance where you can't go backwards in time, and we need to think more creatively about how we solve these problems. Okay, so that's all I really wanted to say about going forwards and backwards in time. What I wanted to end with is something that Alain touched on, and that's the more humanitarian aspect of some of the things that I work on. So some of you might be aware, about 25 years ago now or so, UNICEF launched an initiative to provide clean, safe water for residents in Bangladesh. And the idea was that they would drill boreholes into the ground so that the Bangladeshis could tap into the groundwater and drink this groundwater rather than the contaminated surface water. In principle, this was a great idea. In practice, it turned out to be a disaster because the groundwater is naturally contaminated with arsenic. This has been described as the largest global mass poisoning. It's affected more than 3 million people so far. But there may be a solution, and the solution comes in quite a simple form. It comes in this readily available laterite soil. Now, laterite is very iron rich, and you can see that this is red, very red soil here. Now, iron absorbs arsenic, which means that you can take a filter. I can fill up a cylinder like this, full of this laterite soil. I can take some contaminated water in this dustbin at the top here, and this is contaminated to 100 times over the safe limit of arsenic. And it filters through just through percolation, and what you get out of the bottom here is pure water. So it's incredibly effective. But we ask some questions here, such as, how do we know when this filter has expired? It's not like your Brita water filters that you replace every 3 months or so, but if you don't replace them, it's okay, the water just doesn't taste so good. Here, if you don't replace this, then you're drinking contaminated water that could potentially kill you, and you don't know until a year or so later down the line. And how do we upscale for a school or a community? This is a home filter, and this is the filter that's actually in my postdoc's home in India. But if we wanted to upscale, we need to have some mathematical models to understand how much material we might need to use. So I should check the volume on this, but you've heard me talking quite a lot, so I'm going to give you a respite from me talking. I'm going to show you a video, and the video is of me talking. What we're trying to do really is develop mathematical models that can help purify water all over the world. Arsenic contamination and other contaminants, it's been described as the largest global mass poisoning. It's affected more than 3 million people. Using a very simple, readily available laterite soil, which is this stuff here. Because it's readily available, that makes it very cheap. And then you take the contaminated water, and then it passes through this column of laterite soil, which is about a metre or so high. And what you get out of the bottom is almost pure water. If you run this filter for a long time, eventually the filter cannot soak up any more arsenic. It's becomes saturated. And so the key question that we're trying to address is how long before we need to replace this filter? You cannot run an experiment for 6 or 7 years to work out how long this filter would last. So we need to have accelerated tests, and running them on a computer gives you that test. What we wanted to do with our mathematical modelling is take something that is a very complicated problem and reduce it down to something very simple. But what you want to know ultimately is what is the concentration of arsenic in the water that comes out. That's all you really want to know. Ideally, we wanted to be able to explain the whole problem in terms of a single parameter. So this number relates to how much mass of soil you're using and the required flow rate and the absorption capacity of the soil itself. The typical exchange rate at the moment is about 5 or 6 years. Our predictions say they can last to maybe 7 or 8 years, so it gives you a little bit of extra time for these filters. The key point of our models is that now if you want to make another filter for a particular size school or something, then anybody who comes in and says they want a filter with a particular flow rate, we just give them the number and say this is how you would make that filter. So we're trying to make something that alleviates all the complications in the problem. For me, innovation is very important. I'm a very applied mathematician, and that means that I interact with a lot of different industries. And that's a good way to find out exactly what the key questions are. I think as mathematicians, we can get a bit caught up on some of the fine details that we find interesting that might not necessarily be the key questions. So working with industries, working with experimentalists and the wider scientific community is a good way to keep us grounded and make sure that we are innovating. So what's the state of play with these now? Well, we have some filters in family homes. We have filters providing schools at an order of magnitude of water per day. And another order of magnitude higher is in communities as well. And now we're looking into the removal of fluoride as well and reactive dye. So most of you are wearing clothing that has been made using reactive dye. And once this has been made, it makes a lot of wastewater, which is then just pumped straight out into the water stream. So trying to remove this dye is pretty complicated, and it's carcinogenic as well. Okay, so before I show my summary slide, I should acknowledge some people. All of the stuff that I do is in collaboration with lots of different people, as is all of the work that we do here in Oxford. So with that, I would like to conclude, and this is kind of a broad picture of the sorts of things that we have looked at here and how you can go backwards in time with all of these. I hope you don't want to go backwards in time for the last hour and wish that you want to go somewhere else, but I hope you've actually learned something from what I've talked about today. Thank you.